type out your codes there. That's all. Okay, so if yeah, okay, fine. So then let's move on. Uh, so now we can start NumPy.
Should I share my this? Okay.
Sure, yeah, do it. Yeah. Yeah, Gayatri. Yeah, yeah, it's nice. Yeah. So you're using multiplication as well,
Yes.
printing out the values. Yeah. So you're already familiar with Python.
Yes, sir.
Okay, fine. And have you used this one, Jupyter Notebook earlier?
Yes, sir.
Okay. Yeah, then people who are familiar with Jupyter Notebook, then there is nothing much. It's just the collab environment that you need to be aware. So now let me switch over to my screen. We will start the NumPy. So I think I have already asked you all the participants to upload the folder that I had sent. So you have to unzip it and then upload it as a folder into your Google Drive. So even though your name, the name that you have given or what I've given there would be different, but essentially you have to get into it. So you have to go into your NumPy folder. Okay, so and then you have so you can run the NumPy there. So I have in a different folder over here. So you can start with this numpy.ipynb. So you can go there and double click on the numpy.ipynb, and you should be able to open this collab notebook. So I'll just wait for 2 minutes. All of you load this particular file on Google Colab, and if there is any problem, let me know. Coordinators, so it is there continuously up to 1, or is there any break in between?
No breaks, sir. It's continuously up to 1.
Okay, fine. So are you able to open this particular file and load it into Google Colab?
Yes, sir.
Um, any comments from participants that anybody has any difficulty? Okay, I hope that all of you have been able to open this file. So NumPy is basically a mathematical library that is there. It's again an open source library built around Python, where you can do most of the mathematical operations, very similar to MATLAB. Any doubt?
Actually, I have upload means all the three zip files I have added to the drive. What is
Yeah.
actually I'm not
No,
getting.
you have to unzip it and then upload it.
Okay, unzip and then upload.
Yeah.
Okay,
Okay,
means
Yeah, you should be
from
able to see the folder something like this.
okay, sir. I have uploaded.
Okay.
uh, so in the collab itself, no?
I mean, you have to upload it into your drive basically.
Yeah, I have uploaded it.
Okay, so then you can click on a particular folder name, no? So and then you can enter inside that. See
Okay,
that.
okay.
So like NumPy should be your folder. So in my case, it's slightly different. So when you double click it, you will be able to see all these files over here. When you will have 3 or 4 files, so you'll be
Four
able to see this.
files.
Yeah, so you will one of the file name will be numpy.ipynb, and on the left you should be seeing this sort of infinity symbol, which is a collapse symbol. Are you able to see that?
Yes, I'm just doing it.
Yeah, so you can double click on it. Once you double click, automatically the file will open up in another
Yeah.
tab.
Okay, sir. Thank you.
Okay. So, but you will have to import, like unlike in MATLAB where most of the toolboxes are, I mean, when you start up the MATLAB, it
Sir,
keeps loading.
someone is presenting that screen, so we are unable to see your screen.
Uh, I don't know. I mean, I am sharing, no?
Why don't you subdivide your screen into half? One on for your work and the other one for the screen for the from the instructor.
Or you can just look at my presentation right now, and then I'll give you time so that you can go back and work on it. That's also fine.
Okay, okay, sir. Continue.
Yeah. So here you need to call the libraries. So that is why you call it using the import keyword. So import numpy. So and then to simplify it, we just give some alias, some alternate names to it, so that every time we call function.
Sir, we are not able to see your screen, sir.
Sir, we are not see your screen.
I was sharing. I don't know why again. Is it? Is it?
Yes,
Are you able to see?
yes,
Yeah.
yes.
Yes,
Okay.
sir.
Okay. So now import. So this is the first code block which is there. Import numpy as np. So import is the keyword that you need to use to import the library, which is the numpy library. And I mean, if you are doing offline in Jupyter Lab and other stuff, so when you install Python, so typically this NumPy, Pandas, and other scikit-learn and other libraries will automatically get installed. Similarly, in Colab also, the basic Python package has got the NumPy library. But yeah, but every time you want to use it, you need to use the import function numpy as np. I mean, this is an alias. You can give any sort of name to it. It just simplifies the whole work. And you run this code block. So again, since you have opened this, this is a new notebook that we have opened. It will start. It will say connecting. So it will take some time to connect and initialize, and then give you the required uh, hardware. So now it's a connector, and then after connector, it runs. There's no output over here, so it just runs it. We will start to look at NumPy through the arrays and array manipulation. Yeah. So one of the basic things is about array creation. I have used one variable name called var1, and the NumPy has got a function called array. So every time you need to access it, you access it through the alias name that you have given here, np, then say dot. So it's more like a class, so that you are calling within this from this class a function. So np dot array. This syntax is it's important to preserve. So an array, so you open the braces, and then within a square bracket you have to define your array. This is a simple 1D array which is there, and then you can use print. So we say print. One way is just to put var1. Otherwise, you can use the function called print and print var1, and you will be able to see that array getting printed. Okay. And how do you access the elements of this array? So in Python, all the indexing starts from 0. So the first index is 0, 1, 2. So if you want to access the first element, you say var1, the variable name, and then again the square bracket with the index that you want. So you can change your index here. And as per that, you will get the values which corresponds to that particular index. So, I mean, these are the basic structures that we are going through. It's more of a programming context, but then eventually we will get into the mathematical aspects as well. So then in the next thing is from one-dimensional array, we move on to n-dimensional array. In an n-dimensional array, what you have to note is that we have additional square braces. So this becomes one first row and this becomes the second row. 1, 2, 3 is row 1, 4, 5, 6 is row 2. But again, the definition is np dot array only. So you print it. So this is how a two-dimensional array you have created. So pandas also is another library where some of the basic things about basic structures such as arrays, lists, and other stuff which are there, you can also do in Panda. And Python itself has got all the basic structures. But we are specifically using NumPy because what is not there in the core Python or in Pandas, the mathematical manipulation packages or functions, they are available in NumPy. So that is why we are focused on NumPy. So, and you want to know what is the size of this matrix. So you say you can use this syntax. So variable name dot of shape. The shape is going to give you the size of the matrix. So you just print it. So you now see that var2 is now 2 rows and 3 columns. So 2 by 3 is the size of the array or matrix var2. So it's basically a matrix, but it's all defined as an array in NumPy. Then this is okay. This you created by hard coding all the values. There are other ways to create the arrays as well. So do you want me to go through few more cells and then you want to do the exercise, or you want to take some time off now for 5 minutes and then again we continue? Coordinators, what do you prefer? So should we let the participants try out for 5 minutes?
Yes, sir. You just try out for 5 minutes. If they're familiar, then we can move on. Is that okay, sir?
Yeah, sure. So
Thank you.
yeah, so 5 minutes, so 12:15. So again we'll continue.
Yes, sir. Yeah, sure.
You can ask any doubts in the meanwhile.
Participants, any doubts you can just interact with, sir.
Yeah, tell me. Hello. Uh, I didn't hear you. Yeah.
Sir, there is a question from one participant. Sir, please show the command numpy.
Command?
Numpy.
So there's no command, and this is where you import the library. So you already have it in the code, which has been shared with you, the file.
Sir, there is one more question. How Collab is different from Jupyter Notebook?
They are almost one and the same. There are some additional features, some top-up features which are there in Jupyter Lab. So some of them will be missing here. Otherwise, they are same. And when you use Jupyter Lab, you are using your own resources, hardware resources, your CPU, your memory, and all that stuff. But here, this Collab runs on Google servers. So you get to use the CPUs, GPUs, which are there on Google server, remote. So if anybody wants to get started with Python programming, so it's very easy, and especially since you are all so so you are going to teach your students. So it's a very quick start way to get them on So you don't have to, there are no hassles of installing Python libraries, that, this, and other stuff. So you can just focus on what is required.
Yes, sir.
Give me a minute, I'll be back.
Mm.
So now everybody is familiar with these things.
Yes, sir. I think we can continue.
Okay. So the next thing is that we look at other ways of creating these arrays, and one of the function is called arange. So when you say arange, it starts with 0, and then it generates a number until which has got a length of 12. So when you say arange 12, you start since the index starts with 0, so from 0 it goes up to 11. These are typically used in the context of when you want to create or when you want to run loops and other stuff. The arange function is quite useful. And the other way, like just like in MATLAB, so you have this linspace, log space, and other stuff. So when you say linspace, yeah, other thing is that you can hover over these things, and then you'll also get some understanding of what this function is, and then what are the different sort of input variables to this function. So that also you can see when you hover over your mouse over that particular function name. So the linspace 10, 105 means it creates a number which starts from 10, and then there are 5 numbers in between 10 and the last number 100. So it automatically spaces the numbers linearly, subdivides linearly 5 divisions, and then generates this output. So this is the np dot linspace. So everywhere you're using np dot. So that is how you can call any of the functions which are related to NumPy.
Just, I mean, the line space is dividing.
Basically, it is 5 equispaced numbers between 10 and 100.
Yeah. Okay.
Okay. Then other things which are familiar in MATLAB also is that ones and zeros. So you have that. So when you say ones, it creates a matrix of identity, not identity matrix, the value with one. So it's a 2 by 2 matrix. So np dot ones. So 2 by 2 with all variables with one.
Uh, Sir,
Yeah.
actually, all the numbers are represented as one dot. So by default, it takes floating point numbers.
Yeah. So it is going to consider floating point.
Okay, so in regular Python also, it will do the same thing. Means if I go for any Jupyter notebook,
Yeah.
then
Jupyter Notebook also it will be the same. Means the Jupyter Notebook or this will not be different in that sense. But
okay.
when you talk about what is in Python versus what is in NumPy, there
Huh?
can be differences between them. So,
Oh,
so this is
okay.
particularly with respect to a NumPy library. This is the output that you want to get. But
So
yeah,
yeah, if we need an integer values only, then
then there is something called typecasting that you do, no? Typecasting. So you can use the typecasting functions and then probably convert this floating to integers.
okay. Okay, sir. Thank you.
Yeah. Then np dot zeros is similar, where you are creating instead of ones all matrix with zeros. So again, these are subtle differences. So how you can put them? So these things shouldn't matter much, whether it is a square bracket or a simple brace. And one of the most important things that I would be using is the random function. So the np.random. So the random itself has got its own functions. So one of those functions is rand. So you have to generate 5 random numbers. So you can use this np.random.rand. So instead of 5, you say 15. Then you can generate 15 random numbers. Again, here itself, there are multiple other controls and multiple other functions which are there, uh, where you can also force it to have integer sort of random numbers as well within, and also you have no control. It is between 0 and 1. It's going to generate the random numbers. But if you want to say generate a random number between say 10 and 20, so there are functions where you can even control the way the random number is generated within your range and the way you want it. So this is about so all these things are simple ways of creating arrays: a range, linspace, ones, zeros, and the random. So now, how do you access? The next step is how do you access and manipulate the arrays? Yeah, so now we have around 40 minutes. So I will, anyway, now since all of you are familiar, I will just go through it at a quicker pace because we also have to get into some other matrix manipulations later on. So how do you access and manipulate the arrays? So now we have already defined a variable called j. So just let's print it. And now you want to access three variables within the array called j. So that you can say colon 3. So since this is a one-dimensional array, so it takes by default it starts from 0 and it prints 3 values from the starting index. So 3 does not mean the value called 3 or something like that. It is up to 3 uh, what is called the positions that you're going to get array index. So three indices are printed when you say colon 3. Again, you have to remember the square bracket here when you're going to call it. And suppose you want this itself, the syntax can be extended. So this syntax, when you extend it as 0, 10, 2, it means that you want to extract from this J array from 0 to 10 in steps of 2. So, and that is how you have extracted all even numbers from this array of called J. Then other option is to say 4 colon. So this just works the other way around. Like colon 3, it starts from the first element and goes up to the third element. But whereas when you say 4 colon, you start with the element which is after 0, 1, 2, 3. So this is 1, 2, 3, 4. So it skips those first four elements and then starts with the fifth element and goes up to the end. So that is where you see 4 to 11. I mean, these are basic syntaxes that you need to be aware, and if people are very much familiar with MATLAB, so this might look confusing at the start, but on usage you will get to understand it. So this is how you access the later elements by giving the first the starting value, starting index. So it starts an index after this number and then goes up to the last number. And then now you start basic mathematical operations for it. So it's a scalar addition. So you have this sort of a vector. So vector j, and then you want to add a scalar value to it. So you just say j plus 10. So every element, it's an element wise addition. So every elements, every 10 is added to every element of that array or vector. So you had 0, so 0 plus 10, and 1 plus 10, 2 plus 10, so on it goes. And the next thing is that you could also do addition of two arrays. So you have JJ, which is this, and original J was from 0 to 11. So you can add and create another variable where you have added J and JJ. And this is what will result from it. Obviously, the next step is multiplication. So here when we say multiplication, it does automatically element-wise multiplication. What you would use as dot star operator in MATLAB. So but in NumPy you just use the star, and this will give you the element-wise multiplication. Okay, so that is one thing to know. On the other hand, if you want to do a matrix multiplication, or the dot product. Dot product is going to be dot product of two vectors is going to give you a scalar. So you use the dot function. So j dot 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 jj. So then what it is going to do is in a typical vector dot product, the how it's going to operate. So this is going to give you a scalar value by doing a dot operation on the vector j and the vector jj, and that's why you see a single number when you say the dot operator. So and this is a dot product. So when you want to do other aspects like cross product, so basically you need to have matrices. So I have defined a new matrix here. Am I going fast or is it fine? So because these are basic manipulations only, so I'm just going through them, and the mathematics behind it is well known. It is just a syntactical understanding that you need to have. Okay, so the next thing is I'm going to define one matrix. So this matrix is yeah.
Sir, sir, what about division? Division.
Division also will do an element-wise division. So if you want to,
But
yes.
some number divided by zero, how is choose that infinity?
No, it will generate infinity for you. So if it is just number by zero, so you can just
Yeah.
this error you will get when you say number by zero. you want to do this thing where you're going to divide. Yeah, so now what you see here is that element-wise division that has happened.
Okay, sir. Okay.
Okay, so yeah. So this the matrix is I'm just going to define. So instead of ones, I have multiplied it with by scalar value 7. So I get a matrix of all sevens. Okay, so this is the matrix 3 by 3 matrix of sevens, and I'm going to generate a second matrix of tens. The 3 by 3 matrix of tens. So 10 into np dot ones, and I'm going to define the size of that matrix. Now this is where the dot product and other things has got more value. So you say dot product. So this is basically mat1 dot mat2 is the basic matrix multiplication. So that's what you can get here. So it has multiplied the matrix all sevens with all tens, and this is how you get do matrix multiplication. This is one of the ways of doing matrix multiplication in NumPy. So of course here when you are saying mat1, mat2, here earlier I think you used j dot dot. Okay, the same way you are using here. So now mat1 is a matrix, it's a NumPy matrix. Mat2 is a NumPy matrix. So you are multiplying matrix 1, mat1 dot dot with the second matrix, which is mat2. So this is sort of a perfect way of doing matrix multiplication in NumPy. But other simplistic another method which is there, sort of straightforward way of looking at it is at. So instead of dot dot and all that stuff, so mat1 at mat2 will also give you the same result that you saw here. So mat1 dot dot mat2, the another equivalent way of doing matrix multiplication is mat1 at mat2. But you need to know what is happening. So what is basically happening is it's a dot product that is happening. So that is why this is a sort of a pure way of looking at how this matrix multiplication operation is happening. This is quite important, matrix multiplication. Then other things that you can do with arrays and matrices is sum. So you want to sum of all the elements of the array j between 0 to 11. So that when you say dot sum, so it's going to sum all individual elements and going to give you the output. And you have similarly max, min, and so on. So max will give you the maximum value that you have in that array. You can do it on matrix as well. So this is just j. So if you would say what was the matrix here, mat4. Say mat4 here. It's going to give you the maximum since all the values are the same. So it's just 2 times the maximum value, and that's what you're going to get here. Okay. So that is about basic array matrix mathematical operations on matrices. So that is what you saw here, starting from scalar addition, scalar multiplication, then dot products, then element-wise products, and other aggregation functions. So these are sort of aggregation functions, so sum, max, and other stuff. So that this is a typical usage. Then you can just see the last aspect, which could be sort of relevant, is the sorting. So I was telling you earlier also that in using there are other functions in random which can generate random integers within the range that you want instead of between 0 and 1. So now the rand int, instead of random.rand, you use rand int. So this will give integer random functions values which are between 1 and 10 of the size 3 by 3. So this is how you can use it and then create this random integer. So now this random integer has been generated. Now we would like to sort it in some ways. Say sort the rows in ascending order or sort the columns in ascending order. So for that, the NP numpy gives the sort function. So you np dot sort and whatever is your variable, the matrix here is C, and access is equal to 1. So when you say access is equal to 1, it's going to sort it with all the rows in an ascending fashion. Okay. So now 826 became 268, 832 became 238, 255 is already in an ascending order, so it remains so. And if you want to sort the columns in an ascending order, you just change the axis equal to 0. So then 882 is 288, 235 is already ascending, 625 is 256. So this is how you can sort the variables in NumPy. Okay. Again, you can even change ascending to descending by adding more options here.
Sir, is possible sort in diagonals?
What you want?
Diagonals. 8 instead of pi instead of 8.
You want to swap or you want to create a diagonals in an ascending order?
No. Sort. So instead of row and column, same as here.
No, diagonals you cannot directly sort. You would have to write your own code to do that.
Okay, sir. Okay.
I mean, these are sort of basic structures that any language will give. And beyond that, you will have to make your own codes to get what you want. So this is, I think, sort of an introduction to NumPy. And there are some more which are there. So I'm not sure if I can give you 5 minutes break now to work this out. Probably after the session or later on, since the codes are available, you can practice it. So I'll move on to the next notebook over here. So NumPy SciPy LA. So you can also open this or just to go through my screen. So NumPy SciPy. So I mean, the SciPy is basically the organization which generated many of these libraries. So some of the features, if you look at the notebook that I have shared, so it's going to tell you what is the difference between NumPy and SciPy. But both are scientific calculation libraries. SciPy has got certain advantages. So that is why I'm going to show some functions which are relevant in SciPy. So SciPy has got the linal, the linear algebra routine. So you call that SciPy's lin alt. So you have to import it again. So import SciPy linal as LA. So just a shorthand for it. Okay. So I think maybe you can open this one, the second one, so which is available in your folder, Google Drive folder. So you'll be able to see this. Okay. So here, what we are going to do is we are going to take it one step further, in the sense that we will do some of the linear algebra manipulations, which are relevant to what you're already being taught in the mathematical sessions that we taken earlier for you. So whatever those things are there, you can come and practice them here in the collab environment in the using NumPy and SciPy. So now having understood how to create a variable, how to create an array, how to create a matrix, how to access elements of an array or a matrix, how to do basic manipulations, sort of array or matrix manipulations like scalar addition, multiplication, matrix multiplications, and even sorting. So now it's now time to look at doing some of the linear algebra related stuff here. So I want to compute this sort of matrix value, which is 8 times A. Now A, B, and I are matrices. I is an identity matrix. So I will define what A, B, and I are, and eventually I want to compute this value 8A minus 5B plus 6I. So, this code block below is going to show you how to do that. Matrix A is np.array. So I have defined a 2 by 2 matrix. So 6, 4 is the first row, minus 3, 8 is the second row. If you want to print and see it, so I have just given you the sort of, instead of just putting A, I have given in quotes. In quotes means it's going to print those characters out, and then eventually the matrix. So this, then we have the matrix B, again a 2 by 2 matrix, and I'm just printing it, and identity matrix. So how you define an identity matrix is I function. So you saw ones function, zeros function. This is I function for identity matrix, EYE, and again this is 2 by 2 matrix. So when you are doing a basic matrix algebra, so you will have to maintain the sizes of the matrices. So all the matrices are 2 by 2 size. You can just run it and you'll be able to visualize the matrix A, matrix B, and the identity matrix 1001. Now, calculating this value 8A minus 5B plus 6I is as simple as that, as simple as just 8 star A minus 5 star B plus 6 star I. So what basically we are doing is 8A is a scalar multiplication, 5B is a scalar multiplication, 6I is a scalar multiplication. Then we are doing the matrix subtraction, matrix addition. That is what is happening. Yeah. So basically, the priorities also are fixed. I'm not putting any quotes over here. I'm not bifurcating 8A, 5B, and 6I because I don't have to do, because the star operator has got a higher priority than a minus operator. So 8A is going to get computed first, 5B next, 6I next, and then in any sequence, if the subtraction or addition happens, it doesn't make any difference. So this is my resultant value of my operation with matrices 8A minus 5B plus 6I. Okay. So this is my operations. And how can you do it even other way around? I mean, now we just had individual scalar multiplication of the matrices, but what if there is a matrix multiplication? Like this is an aspect where we are doing 3AB minus 5A. So now AB is a matrix multiplication. So you have two ways to do it. So A dot B or A at B. So, and you have to ensure that that the matrix multiplication rules are followed. In the sense that if you say Mn, then the second matrix should be N something, so Np or something like that. So you that sort of whatever caution you have to take when you're doing matrix multiplication, you have to take, otherwise it will throw up an error. So this is how you compute this value 3AB minus 5A. Yeah, so I mean, these things are quite simple. I mean, people who are only with C, C++, and other stuff, so you understand matrix multiplication is, sorry, matrix multiplication is slightly more complicated in C or C++. But MATLAB makes it too convenient, and if you're already aware about MATLAB, then this doesn't look anything great, but it just simplifies the whole process. Any doubts?
No, sir.
Okay. So the next important thing is that how do we do matrix powers? There is a specific function that you need to call. And here again we are switching to NumPy. Yeah, I mean, if you saw here, until now we are still not using anything related to SciPy. We are still sticking with NP. So with NumPy itself, we are able to do all these computations. And for matrix powers also, you have that numpy.linalg. So the linear algebra routine within NumPy, there you have again a class called matrix power and a function called mpow. So you use that mpow function, so mpower, matrix power, and you call what is the matrix that you want, and then what is the power you need to give to that. So I want to square A. So the A square is called this way, mpow a comma 2. Okay, I didn't run this code cell, so that is why it threw up an error. So you could call these routines at any code cell, but you have to ensure that they are running. So now that library is there. Now you run it, you're good. You can get the required value. So this is the matrix power. Okay, so we have another 15 minutes. So there are some still some basic things which are there. So we'll go through it, and then some visual sort of linear algebra is the third one which I wanted to show. So let's see how the time goes. If it takes some time, then we might have to push it to the next session. Okay. So this transpose. So matrix transpose, you call it using the dot operator. So, so A and B are NumPy defined matrices. So now B dot T. So dot T is what is going to do transpose. Okay. So now A and B are both 2 by 2 matrices, so it doesn't bother. So if I transpose it also, it's still going to be B. I mean 2 by 2 only, and hence I have no issues. I can do it. So if you want to just compare this to the actual A matrix A multiplied by B, so it would have been this. So how is B matrix defined? So B matrix is defined in such a way that AB and the AB transpose are going to give you the same value. I mean, you can try it out with the different sort of values. You want to see the difference between A times B transpose versus A times B. Okay, so this is about transpose, and other important thing is that inverse. Okay, so inverse, you need to call the value called LA dot in. So this is a matrix A that you're having, and you want to find the inverse. So when you just use dot inverse, this inverse should exist. Okay, which means the determinant is not zero and all that whatever conditions are there, so it should be satisfied. So then this LA dot in will work, and you can get the inverse of the matrix. So how do you verify that this is the inverse of A? So let me say this.
Again inverse.
Okay, yeah, that's also possible. And or what about A times A inverse? So you should get an identity matrix. So that's how you are ensuring that you have found the right inverse. Okay, so that is one of the way to use or to find the inverse value. So LA dot in.
Sir, suppose
Yeah.
suppose singular matrix, what is shows the error?
Yeah, we'll have to find out. Is there can you give me a example of a singular matrix?
A determinant of A 0. That's
Yeah, I mean, if you have an example, so then I can work it out.
2 1 2 1. First row is 2, 2. Second row is 2, 1, 1.
I'll just copy this. Go to 1, 1.
2, 2, 1, 1. 2 minus 2, that's 0.
Okay, so now you want to see what is going to happen with inverse. You get an error. It says singular matrix. So you can't use when you don't have the .inv function cannot give you the answer. That is where you need to switch to pseudo inverse. If you still need in those conditions, you get a pseudo inverse.
Okay,
So
sir.
that is where you can use the again from the SciPy library linalg. So la.p in. Okay. So now instead of a, let's say y. Okay. I've done it. So what gave you as an error as a singular matrix using just la.in is going to give you a pseudo inverse with the PINV function. So there are two functions here, PINV, which is a least square solver, and PINV2, which is a SVD based method, singular value decomposition based method. Okay. So you can try that. So la.pinv2. So both are giving you the same result, the least square solver as well as SVD. Okay, so the next thing is the trace. So you have matrix A and you want to find the trace of that. So where is the matrix A? Okay. Let me just again put the matrix A here. So A is 6, 4 minus 3, 8. And what is trace? Trace is the sum of the diagonal elements. So 6 plus 8. So that is 14. So that's what you got from the function np.trace. Similarly, you have norms, the norm of a matrix. So you just use the function called la.norm and you're going to get the norm of that particular matrix. So I think some of these things should have been touched in your theoretical sessions earlier, trace, norm, and all that stuff.
Yeah, we have calculated eigenvalues that time use that trace.
Yeah, yeah. So yeah, so that is the reason I have collected whatever is relevant in the context of the linear algebra and eventually the machine learning. So I'm just showing those particular functions only in NumPy, SciPy, and other stuff. Yeah. So other important thing is the determinant. So if you want to say the determinant of the matrix A, so then LA dot. So dot det. So DET. So that will give you the determinant of the matrix A. If the determinant, yeah. So I mean either it exists or it can be 0. So anyway, it's going to show you the determinant. Just give me 1 minute. Okay, so this is a DET function that you use. They're using the SciPy here. So SciPy is linalg, so LA.DET. Then other important thing is the matrix rank. For that you import in the NumPy linalg. There is a function directly called matrix rank, and you will be able to see the rank of that matrix. So an identity matrix of 4 is a full rank matrix, which should give you the this is a 4 by 4 matrix, 4 by 4 identity matrix, and since all that's what you should have known from the linear algebra some of the theoretical aspects is that see all the rows and all the columns are independent there, so that is why it's a full rank matrix. And so the identity matrix will give you the size of the matrix, which is 4 by 4. So this is also 4. But if you had some dependencies, suppose some columns or the rows were dependent, then you will see the rank of the matrix is not equivalent to the size of the matrix. So for that verification, you can use this matrix rank function. Okay. So we have 10 minutes. I think that's what we're able to do. We'll be able to cover some of the decompositions right now. So these are important decompositions which are relevant in the context of linear algebra and machine learning eventually. So LU decomposition. So in the SciPy linear algebra routine, you call function called LU, and it is going to decompose a matrix A into 3 values. So the lower, upper, and one more additional matrix, which is the P matrix. Otherwise, basically, LU decomposition is you decompose a given matrix into lower half. You see here the lower half is a 2 by 2 matrix. So the lower half is the upper half are all 0. So this is the diagonal, and then diagonal and the elements which are below the diagonal only will be there in the lower half or lower matrix. And in the upper matrix, you have diagonal and the upper elements. Okay, so that is how you have split a matrix A into two or fundamentally two components, the lower component and the upper component. So the LU function will give you that capability to do it. Similarly, we have QR decomposition. So for that, like you got LA.LU, now we used LA.QR. So the advantage of QR is that, I mean, in LU decomposition, you need to have a square matrix. Suppose you are having a non-square matrix, that is when you get into the QR decomposition. Just a minute. Okay, so in the non-square matrix, in the QR matrix, so we have so np.array. So 7, 8, 9, and 34, 90, 45. It's a non-square matrix. Okay, so now you can do a QR decomposition on it. So you will have one square matrix, the Q, and the residual matrix, which is non-square. Okay, so that is how you can do a QR decomposition of a non-square matrix in using this NumPy and SciPy. And other important decomposition is Chomsky decomposition. So you have this array now, so a 3 by 3 matrix, and you call Chomsky here, and you can get an upper triangular matrix over here with Chomsky. And then if you want to recover your original positive definite matrix, then you say U dot transpose multiplied by U. So originally 73373 and 337. So you're going to get back that positive definite matrix. So Chomsky decomposition typically used for positive definite matrices, and this is how you call the Chomsky for that particular thing. Okay, and Chomsky, we define it as an upper. You can also do a Chomsky decomposition in terms of a lower triangular matrix and recover back the original positive definite matrix as L multiplied by L transpose, LLT. LL transpose, so UU transpose. So basically your K is equal to UU transpose, which is equal to LL transpose. And that's possible with a positive definite matrix. I'm not going to get into the definitions of positive definite matrix and all that stuff. So I hope you know that, and this is how you can sort of utilize it over here. And the other important thing is eigen decomposition. So you call the eigen function here. So when you call eigen function, you can get two things: the eigenvalues and the eigenvectors. For the matrix A, so these are the eigenvalues. Okay, so you're getting a complex number over here. So eigenvalue 1, eigenvalue 2, and the eigenvectors that correspond to the matrix A is this. So this is the eigen decomposition using dot EIG function in SciPy linear. The last one is you solve linear system of equations. So this is fundamental because this is the linear system of equations. The solving this is what most of the machine learning is about, especially the linear regression of it. So you define an array. So I have just defined an array 4, 5, and already have a matrix A. So now AX is equal to B. So that is how you can have a system of linear equations. Okay, Ax is equal to B. Then you just say LA dot solve. So you can use just the solve function. So of course the matrix has to be, I mean here it is a square matrix. Then when you say solve A equal LA dot solve A comma B, so it's going to solve for x's. Okay, so x1, x2. So two values. So it has actually solved two simultaneous linear equations. So yeah, so that's the thing about what you do with basic linear algebra sort of computations using NumPy and SciPy. So we started with basic calculations, moved on to powers, transpose, inverse, and pseudo inverses, trace, norms, determinants, matrix ranks, and then LU decomposition, pure decomposition, Cholesky, Egan decomposition, and system of linear equations. So that should put you on good footing when you want to apply algorithm learning. Yeah, so I'll stop for this session here. Any doubts?
I don't think so. They have, sir.
Okay, so then fine.
Yes.
We'll
We
meet
should meet at 3. Yeah.
at 3 o'clock. We will. So let's see. I mean, there are some geometric transformations which were there. We will keep it to the end. So let's probably jump to the scikit-learn based linear regression in the next session.
Okay, sir. Thank you so much.
Thank you.
Thank you, dear participants. We shall meet at 3 again.